So in parts 3 and 4, we're going to look at how to add vectors both by hand along with in MATLAB. And remember that when you're adding vectors, although the definition is defined from a geometrical perspective in terms of either the triangle or parallelogram rule that we spoke of, it's much easier to do it if they are decomposed into rectangular form. Because when they're decomposed into rectangular form, basically all that you're doing is creating a new vector, which has an x component, which is the sum of the two original x components, and a y component, which is the sum of the two original y components. So kind of just finishing off what I was doing here to complete my calculation, you'll notice that in our case for V1, and remember you are doing this for V3 and V4, I hate to keep repeating that, but I always get submissions that are just basically a duplication of what I did here. So you want to go through and do the same process for V3 and V4. So you can use these formulas if you want. Plugging in magnitude of V1 is 2 cos 0, and that is the x component, and 2 sine 0, that is the y component. However, if you put these into your calculator, not surprisingly, you will find that cosine of 0 is just 1, and sine of 0 is just 0. So this comes out to be 2x hat plus 0 y hat. And if you are not sure how to do that, just go back up into your code that you have in MATLAB now, and remember that you actually converted these to rectangular form as part of your code. So you can just take and, assuming that you haven't cleared your workspace and everything is still there, just type in V1 and you can see it as x component 2, y component 0. Or if you have cleared your workspace and you want to show that again, just take the two semicolons off of V1 and V2. In your case, it will be V3 and V4. And run this, and you'll get the actual the rectangular form of V1 and V2 right here. So just finishing off here, V2 technically, you would get using the same formula, magnitude times cos for the x component, and magnitude times sine for the y component. And when you plug that in, that would be 3, I know you can't see me right now, see what I'm writing, 3 cos 45 plus 3 sine 45. I just basically want to finish it all off, and then I will show you the .cam. But the cos and sine of 45 is 1 over the square root of 2. That's why this is coming out to these weird numbers here. And I'm going to round to 3 significant figures. You feel free to do that too. But there we go. And sorry for the little bit of scratch here. I was trying to write, actually I'm going to scratch that whole thing out just to not confuse you. Rounded to 3 significant figures. The x component of V2 turns out to be 2.12, as does the y component. And not surprising that the x and y component have the same magnitude, because if we look at this vector, if we were to decompose it by dropping a perpendicular to the x-axis, it kind of has equal magnitude x component and y component. That's what it means to be at a 45-degree angle. So in terms of computing the resultant or the sum vector, VR equals V1 plus V2, what I want to show by hand here is that if I have both of these decomposed into x and y components, all that I want to do is add each of those components individually. So the new vector, VR, is going to have an x component, that's the x component of V1, plus the x component of V2. So that will turn out to be 4.12 x hat. And then the y component will be 0 plus 2.12, or the y component of V1 plus the y component of V2. So that is the resultant vector in rectangular form determined by hand. So all that I'm going to do now is just to show in MATLAB. I just need to add 1 line of code, actually, to my script. And since I have both of these variables defined, you wouldn't even have to put it in the script if you want. It's just always good to keep a bunch of code that you're going to use for a purpose contained in a single script file. So I will say compute the resultant or sum vector. And in MATLAB, this is going to be very easy. You just have to give the resultant vector a new name, call it VR as a variable, and assign that variable equal to what you get when you compute V1 plus V2. And I'm going to leave that semicolon off here. And I'm just going to copy this last line and put it directly on the command window. You could rerun everything if you wanted. But notice in MATLAB here, that is nearly identical to the result that we got, only some slight rounding differences. So in terms of what you're turning in for this part, going back to the document here, you'd have your by hand work included right here in part 3. And then for part 4, we want to compute the sum of the two vectors and show the sum using in MATLAB using the quiver function. So we have VR1 plus VR2, and then if you wanted to plot that using quiver, remember that what you need to do is pass into the quiver function, which is QUIVER, the x component of whatever vector you're trying to plot first, comma, the y component. So our x and y component are stored in this variable VR. So I'll take VR and I'll index 1, element 1. So VR parentheses 1, close parentheses. That's going to give me the first component, which is the x component. And then I'll do that same thing to get the y component. And of course, this is exactly what we did when we plotted V1. And you can add some comments here if you want. Plot V1 and then plot V2. So same thing. And I am just going to, sorry about that. It's just telling me I probably want a semicolon when I'm computing this resultant, which is a good idea. So I'm just going to copy the plotting line of code and then get this figure. And you can just include that if you want. Another thing you might want to do, and you're welcome to do it if you'd like, is if you have all this in a script, you can just add that resultant vector onto the same plot by just typing hold on above. And if you think about it, what's basically happening is MATLAB is going through, it starts to generate the first plot, you tell it, hold on, put this on the same plot, and then it makes a computation to get the resultant vector, but then it knows to put it, when this additional quiver command is called, it knows to put that on the same plot as well. And notice if you run this now, you will see all three vectors on the same plot. And you can see this is basically a form of the triangle rule. Right there you have your original vector, V2, here is V1, and if you were to translate V1, its tail, to the tip of V2, let me see if I can knock this out. Sorry about that. Anyways, if you, I don't want to take too much time since I'm recording here. I don't want to make the video drag on too long. But if you notice that first button that I was hitting, that's how you actually can do the save of that if you want to kind of insert a larger, higher resolution figure. However, this is good enough for our purposes. You can just take and when you were asked to plot the sum of the vectors in MATLAB, you can just have that. And then for the actual result of computing the resultant in MATLAB, you can just take and, if I were you, I think the easiest thing to probably show would just be an actual VR equals V1 plus V2. That way you can actually see the resulting components there. And part of what's screwing me up is I'm trying to zoom in to make this more readable for you. But if you have just VR equals V1 plus V2, obviously I will know, and remember yours will be V3 plus V4, and I will know that you have V3 and V4 correct based upon the part 1 and part 2